In this video, I will explain the residue theorem of complex analysis. The residue theorem helps you to evaluate complex curve integrals along closed curves which circle around isolated singularities of some function. If you want to understand this video, you need to know what a complex curve integral is. You should also be able to identify the three types of isolated singularities before watching this video. I have both a video about complex curve integrals and a video about isolated singularities here on my channel. You can watch these videos if necessary. Before we take a look at the residue theorem, I want to talk about closed curves a little bit. Let C be a piecewise smooth closed curve in the complex plane. We call the curve C positively oriented if the orientation of the curve is counterclockwise. We call it negatively oriented if the orientation is clockwise. Here we have an example of a positively oriented curve. The direction of the movement of the curve is in a counterclockwise direction, so it's positively oriented. Here we have a negatively oriented curve. That curve is oriented in a clockwise direction. We call a positively or negatively oriented curve C simple closed if it circles around each point in its interior only once. Here is an example of a simple closed curve. It circles around each point in its interior exactly one time. Here we have an example of a curve which is not simple closed. If we choose, for example, this point Z in the interior of the curve, we notice that the curve circles around that point 2 times. Here for the first time and there for a second time. So that curve is not simple closed. Let's take a look at the residue theorem now. Let A be a simply connected domain. Simply connected means that the domain A doesn't have any holes. For example, the domain A could look like that. Let C be a piecewise smooth, positively oriented and simple closed curve in the domain A. So the curve C could look like that. Let F be a complex function which is complex differentiable along the curve C and in the interior of the curve C, except for finitely many isolated singularities Z0, Z1 to Zn in the interior of C. So the function f is not differentiable in the points Z0 to Zn, which are isolated singularities of the function f. But the function f is differentiable everywhere else in the interior of the curve C and on the curve C. then the curve integral of f along the curve c is equal to 2 pi I times the sum from k is equal to 0 to n of the so-called residue of the function f at the isolated singularity set k. I will show you how to calculate the residue of a function at an isolated singularity in a minute. But first of all, if you have a negatively oriented curve instead of a positively oriented curve, you need a minus sign here in the formula. So for a negatively oriented curve, you need a minus sign in the formula. So basically, the residue theorem tells you the following. If you have a simple closed curve, which has isolated singularities of f in its interior, you can use the following formula to evaluate the curve integral along that curve. I will now show you how you can compute the residue of a function f at an isolated singularity. So, let z0 be an isolated singularity of the function f. If z0 is a removable singularity, the residue of f at z0 is equal to 0. So if z0 is a removable singularity, the residue of f at z0 is equal to 0. If z0 is a pole of order m, there is a formula to calculate the residue of f at the pole z0. The residue of f at the pole z0 is equal to 1 divided by m minus 1 factorial times the limit z to z0 of the m minus 1th derivative of z minus z0 to the power of m times f of z. So if z0 is a pole of order m, the residue of f at z0 is given by that formula here. In particular, for a pole of order 1, which means m is equal to 1, the residue of f at the pole of order 1 is equal to the limit z to z0 of z minus z0 times f of z. If z0 is an essential singularity, you need the more general definition of the residue of a function. You have to calculate the so-called Laurent expansion of f at the essential singularity z0. That means you write f of z as the series from k is equal to minus infinity to infinity of ck times z minus z0 to the power of k, where the absolute value of z minus z0 is larger than 0 and smaller than some real number r. That's called the Laurent expansion of f at the isolated singularity z0. Now the residue of f at the isolated singularity z0 is equal to the coefficient c minus 1 in the Laurent series of the function. Right now, I don't have a video about Laurent expansions of functions here on my channel, but in most cases you will have to deal with poles of order m and removable singularities anyway. So don't get too confused by that last case of an essential singularity. We will mainly focus on poles of order m. Okay, now that we know how to compute the residue of a function at an isolated singularity, we can finally use the residue theorem to solve some examples. Let's take a look at the first example. Let's consider the function f of z is equal to 2 times z plus 1 divided by z plus 1 times z minus 2. That function has two poles of order 1. The first pole of order 1 is z0 is equal to minus 1, and the second pole of order 1 is z1 is equal to 2. If you don't know why these 2 points are poles of order 1, watch my video about isolated singularities. You will learn how to identify poles of order m in that video. Now we will compute the residue of the function f at the poles of order 1. The residue of f at the pole z is equal to minus 1 is equal to the limit z to minus 1 of z plus 1 times f of z. Here we have used the calculation formula for the residue at the pole of order 1. Now this here is equal to the limit z to minus 1 of z plus 1 times 2z plus 1 divided by z plus 1 times z minus 2. We can cancel this here, and now the limit is equal to 2 times minus 1 plus 1 divided by minus 1 minus 2. And this is equal to 1/3. So the residue of f at the pole z is equal to minus 1 is equal to 1/3. The residue of f at the pole z is equal to 2 is equal to the limit z to 2 of z minus 2 times f of z. Here we have used the calculation formula for the residue at the pole of order 1 again. Now this here is equal to the limit z to 2 of z minus 2 times 2z plus 1 divided by z plus 1 times z minus 2. We can cancel this here, and now the limit is equal to 2 times 2 plus 1 divided by 2 plus 1, and this is equal to 5/3. So the residue of f at the pole z is equal to 2 is equal to 5/3. Now we consider the following curve C1. The curve C1 looks like that. We want to evaluate the curve integral of f along the curve C1. The first thing we should notice is that C1 is positively oriented and simple closed. There are two isolated singularities in the interior of the curve, the poles -1 and 2. So we can use the residue theorem to evaluate that integral. The residue theorem tells us that this integral is equal to 2 pi I times the residue of f at the pole z is equal to -1 plus the residue of f at the pole z is equal to 2. And this here is equal to 2 pi I times 1/3 plus 5/3. And this here is equal to 2 pi I times 6/3, which is equal to 4 pi I. So the integral of f along the curve C1 is equal to 4 pi I. Now we consider a different curve C2. The curve C2 looks like that. We want to evaluate the curve integral along C2. The problem we encounter now is the following. The curve is positively oriented on the right side, but negatively oriented on the left side. Because of this orientation problem, we can't use the residue theorem directly. But we can solve that problem. We split the curve C2 in two smaller curves P1 and P2. So the green part is P1 and the orange part is P2. Now the curve integral along C2 is equal to the curve integral along P1 plus the curve integral along P2. The curve P1 is positively oriented and simple closed. The curve P2 is negatively oriented and simple closed. That means we can apply the residue theorem to evaluate the curve integrals along P1 and P2. So the integral along P1 is equal to 2 pi I times the residue of f at z is equal to 2. And the integral along P2 is equal to minus 2 pi I times the residue of f at z is equal to -1. Don't forget the minus sign here because of the negative orientation of the curve P2. So don't forget the minus sign. Now this here is equal to 2 pi I times 5/3 minus 2 pi I times 1/3. And this is equal to 2 pi I times 4/3, which is equal to 8 pi I thirds. So the integral of f along the curve C2 is equal to 8 pi I thirds. Okay, Let's consider one last curve, C3 now. The curve C3 looks like that. We want to evaluate the curve integral of f along the curve C3. The curve C3 is positively oriented, but it is not simple closed. So C3 is not simple closed, because, for example, the curve circles around the point 2 times. So we can't apply the residue theorem directly to C3, because it is not simple closed. To solve that problem, we split the curve C3 in two smaller curves P1 and P2 again. Now the green part is P1 and the orange part is P2. Now the curve integral along C3 is equal to the curve integral along P1 plus the curve integral along P2. Both P1 and P2 are positively oriented, simple closed curves. That means we can apply the residue theorem to them. The first integral is equal to 2 pi I times the residue of f at z is equal to 2. And the second integral is equal to 2 pi I times the residue of f at z is equal to 2. Because both curves have the pole z is equal to 2 in the interior and are positively oriented. Now this here is equal to 2 times 2 pi I times the residue of f at z is equal to 2, and this is equal to 4 pi I times 5/3. And this is equal to 20 pi I/3. So the integral along the curve C3 is equal to 20 pi I/3. Let's take a look at another example now. We consider the function f of z is equal to z divided by z minus 1 squared. That function has a pole of order 2 at z0 is equal to 1. We want to evaluate the curve integral of f along that curve C. So the curve C looks like that. The curve C is positively oriented and simple closed. It has the pole of order 2 in its interior. That means we can use the residue theorem to evaluate the curve integral. First of all, we need to compute the residue of f at the pole of order 2 z is equal to 1. Here you can see the general formula for the residue at the pole of order m. In our case, z0 is equal to 1 and m is equal to 2, because we have a pole of order 2. So the residue of f at the pole of order 2 z is equal to 1 is equal to the limit z to 1 of the derivative of z minus 1 squared times f of z. Now this here is equal to the limit z to 1 of the derivative of z minus 1 squared times z divided by z minus 1 squared. We can cancel this here. So this is equal to the limit z to 1 of 1, because the derivative of z is equal to 1. And this limit here is equal to 1. So the residue of f at the pole of order 2, z is equal to 1, is equal to 1. Now we can use the residue theorem to evaluate the curve integral. The curve integral is equal to 2 pi I times the residue of f at z is equal to 1, which is equal to 2 pi I. So the curve integral of f along the curve C is equal to 2 pi I. Before this video ends, I want to show you the residue theorem again. If you have a piecewise, smooth, positively oriented and simple closed curve, which has finitely many isolated singularities of some function f in its interior, you can evaluate the curve integral along that curve C by using this formula here. If there are no isolated singularities in the interior of the curve, the integral simply becomes 0. That's the statement of Cauchy's integral theorem. Okay, I hope this video was helpful and you are now able to use the residue theorem to evaluate complex curve integrals. If you liked this video, please consider subscribing to my channel. That would help and motivate me to keep creating videos.